There is a star in the shoulder of Orion. You have seen it without knowing its name. On cold, clear nights, when the sky fills from edge to edge with light, you have looked up at that hunter constellation and found the bright orange-red point burning in its upper left corner, warmer than the blue-white stars around it, softer, like a coal that never quite goes out. Its name is Betelgeuse. It is approximately 640 light-years away. That number is so large that it stops meaning anything almost immediately. But try to hold it.
640 light-years means that the light entering your eye right now, the photons that have traveled across the void, slipped through Earth's atmosphere and landed on your retina in this exact moment, left that star 640 years ago. In the year 1386, the light you are seeing tonight began its journey. Geoffrey Chaucer was writing the Canterbury Tales. The Black Death was still moving across Europe. No one alive today had been born. No one alive then is still alive now. And yet the light that left Betelgeuse in that year is only just arriving. That is the distance between you and that quiet orange star. Consider what 640 light-years feels like at human scale.
If you could somehow travel at the speed of a commercial airplane, roughly 575 miles per hour, the journey to Betelgeuse would take approximately 790 billion years. The current age of the universe is approximately 13.8 billion years. You would need to make that trip 57 times over, back to back, before you arrived. The universe refuses to be comprehended at close range. The numbers always exceed whatever container you try to put them in. 640 light-years is close, by the standards of a galaxy that is 100,000 light-years across. It is practically next door.
And it is still so far away that the word distance becomes inadequate to describe it. Betelgeuse is what astronomers call a red supergiant. It is among the largest stars visible to the naked eye, and by large, the word requires a kind of recalibration. If you replaced our sun with Betelgeuse, if you placed it at the center of our solar system, where our star sits, its surface would extend outward past Mercury, past Venus, past Earth, past Mars, and somewhere into the asteroid belt approaching Jupiter. The Earth you are lying on right now would be inside it. The atmosphere you are breathing would be inside it. You would be inside it.
Its diameter is estimated at somewhere between 700 and 1,000 times the diameter of the Sun. The uncertainty in that measurement reflects the fact that Betelgeuse is not a clean, static sphere. It pulses, it heaves. Its surface churns with convective zones so enormous that individual plumes of hot plasma, each one larger than the entire Sun, rise and fall like slow bubbles in a boiling pot. A star does not have a definite edge the way a stone does. It has a gradient, a pressure, a blurring of itself into space. Betelgeuse blurs dramatically. Its outer envelope is loosely held, barely contained, expanding slightly even now into the surrounding interstellar medium.
And yet, from here, from Earth, from your window on a clear night, it is just a point, just a faint orange dot among hundreds of other dots. The scale collapses at this distance until the extraordinary becomes merely pretty.
The universe does that constantly. It hides its enormity in the ordinary appearance of a night sky. Familiarity creates the sensation of safety. You have seen Orion your entire life, and because you have seen it your entire life, some part of your brain files it under permanent and unchanging. The stars become wallpaper, background. The assumption is that what has always been there will always be there. But Betelgeuse is not permanent.
The light that reaches you tonight tells you nothing about what the star is doing right now. Right now, in whatever sense right now means across 640 light-years of space, Betelgeuse may be behaving in ways that light will not tell you about for centuries. The star in your sky is a portrait, not a window. It shows you what was, not what is. You are looking at the past and calling it the present. That has always been true of every star you have ever seen. But with Betelgeuse, it matters more than it does with most. Because what Betelgeuse is moving toward is something that, when it happens, will not be subtle.
It will not be a quiet change in a number that only astronomers notice. When Betelgeuse reaches its end, the sky above Earth will change in a way that every person alive will be able to see with their own eyes, even in broad daylight. There is something particular about knowing that a familiar thing is dangerous. It is different from being told about a danger that is abstract and remote. The highway is dangerous. Smoking is dangerous. Those things carry weight, but the weight is a statistic. It sits in the prefrontal cortex and feels manageable. But Betelgeuse is up there tonight. It is up there right now, as you listen to this, burning in the shoulder of the hunter.
It has been there every winter of your life, and every winter of your parents' lives, and every winter, as far back as there have been human eyes to look up and notice the lights. And it is dying. Not in a way you will witness. The human time scale and the stellar time scale do not overlap in any meaningful sense when it comes to a star's final moments. But the inevitability is absolute, and the scale of what is coming, what is already in some sense underway, is something that quietly changes how the night sky feels once you know it. The shoulder of Orion is a bomb, a slow one, a patient one that has been there your entire life without announcing itself.
And there is one more thing worth knowing about Betelgeuse before anything else is said about it. The distance measurement, 640 light-years, carries a significant uncertainty. Early estimates placed Betelgeuse at around 430 light-years. Later work pushed that to closer to 700. The most widely cited current figure is roughly 640, but the error bars on stellar parallax measurements at that range are large enough that the true distance could reasonably be anywhere between 550 and 900 light-years. Measuring the distance to a star that large and that variable is genuinely difficult, because the star does not have a precise, stable surface to triangulate from. This uncertainty matters.
Not because it changes the fundamental nature of what Betelgeuse is, but because it affects calculations of how bright the eventual supernova will appear from Earth, and how much energy will reach us when it comes. A star that is farther away is a less intense event when viewed from here. A star that is closer is a brighter, more energetic one. The difference between 550 light-years and 900 light-years is the difference between several plausible futures, all of them spectacular, some of them more alarming than others.
Stars are not immortal. This seems obvious once stated, but the night sky makes it hard to feel. The stars appear fixed, stable, eternal in the way that mountains appear fixed, on a time scale that is so far beyond a human life that the distinction between permanent and very long-lasting collapses into nothing. But every star is burning through a finite fuel supply, and when the fuel runs out, something happens. The mechanism that keeps a star alive, that keeps it from collapsing under its own enormous gravity, is the pressure generated by nuclear fusion in its core. Hydrogen fusing into helium releases energy. That energy radiates outward. That outward pressure holds the star up against the inward pull of all that mass.
A star is a sustained, continuous explosion that gravity is just barely keeping contained. When the hydrogen in the core is exhausted, the star begins fusing helium. When the helium is exhausted, it fuses carbon, then neon, then oxygen. Each stage is faster than the last because each stage is less energetically efficient. Each stage extracts less energy from the same amount of mass. The star works harder and harder for less and less return. The Sun, with a mass of 1, has a predicted lifespan of roughly 10 billion years. It is currently about 4.5 billion years old. It has time. Betelgeuse has a mass estimated between 16 and 19 times the mass of our Sun. It is a very different.
A star of that mass is so luminous, so furiously burning, that it consumes its fuel at an extraordinary rate. Betelgeuse has been burning for approximately 8 million years. 8 million years sounds long. It is not by stellar standards. When life first appeared in the oceans of Earth, stars like Betelgeuse had already been born, burned for their entire lifespan, exploded, and seeded the surrounding space with their remnants, many times over. A red supergiant like Betelgeuse lives fast and dies violently. In the universe's long accounting, it barely registers as a moment. Right now, inside Betelgeuse, the fusion chain is far advanced. The core has moved past hydrogen, past helium, past carbon, past neon. The star is currently fusing oxygen in its innermost regions.
Surrounding that oxygen-burning core are concentric shells of earlier fusion products. Each layer still burning its own fuel, each layer a step back in the chain. Picture it as a set of nested spheres. At the center, an iron core growing slowly. Iron is the end of the line. Iron cannot be fused to produce energy. It requires energy to be fused rather than releasing it. The moment the iron core accumulates enough mass, the pressure that has held the star up for 8 million years will no longer be sufficient. That threshold is called the Chandrasekhar limit. It is approximately 1 4/10 solar masses of iron. When the iron core reaches that mass, gravity wins. Not gradually, not with warning.
In a fraction of a second, in less than a quarter of a second actually, the core collapses inward at speeds approaching a quarter of the speed of light. It compresses from something the size of Earth into something the size of a city. The density becomes so extreme that the physics of ordinary matter breaks down entirely. The question that astronomers continue to debate is how far along this process Betelgeuse currently is. The oxygen-burning stage in a star of this mass can last somewhere between a few months and a few thousand years. The neon-burning stage lasts about a year. These are the final stages before collapse. But final stages by stellar reckoning may still mean tens of thousands of years by human reckoning.
The prediction window for Betelgeuse's supernova is roughly 100,000 years, which means sometime between now and 100,000 years from now, the iron core will reach the Chandrasekhar limit. That is genuinely uncertain. The interior of a star cannot be observed directly. The models are excellent, but they are models. They work from the physics inward, from the physics outward, and they meet somewhere in the middle in a set of equations that describe what probably happens, but cannot guarantee when. There is something almost consoling about this kind of uncertainty. The universe keeps its schedule private. It does not post a countdown clock. Events of this magnitude approach without announcement, or with announcements so subtle that they require decades of careful measurement to read.
And then there is the light. Even if you knew the exact moment Betelgeuse would explode, even if you had the calculation precise to the second, that knowledge would arrive 640 years before you could see it. You could know with certainty that a specific piece of light was already on its way, already traveling toward Earth at the speed of light. And you would have 6 centuries to wait before the sky confirmed it. The knowledge and the experience would be separated by the same 640 years that separate you from the star's present state right now. The universe does not allow shortcuts across that interval. Stars of high mass live short lives precisely because they are so luminous.
They spend themselves quickly. They burn so brightly that the burning is already a kind of waste. A profligacy that is, at the cosmic scale, also a gift. The heavy elements that stars forge in their cores, the carbon, the oxygen, the silicon, the iron, these are the building blocks that later generations of stars and planets are made of. The universe is not hospitable in the ways we prefer to imagine. It is hospitable in ways that require death as a precondition for anything complex enough to be called life. Every massive star that has ever exploded has contributed to the raw material from which rocky planets are built, from which oceans are filled,
from which the particular arrangement of atoms that constitutes a human body is assembled. Betelgeuse is not a threat from another galaxy. It is a participant in the same chain of events that produced this planet, and the water in your body, and the iron in your blood. The most spectacular deaths in the universe are also the most productive ones. There is a kind of strange dignity in this. The star does not simply stop. It does not fade quietly into a dark remnant. It detonates. It gives back, violently, indiscriminately, in all directions at once, the material it has spent millions of years assembling and transforming. The debris becomes the raw inventory of the next round of construction. New stars, new planets, new chemistry.
New arrangements of atoms that will, in some cases, and over the fullness of time, look up at the night sky and wonder about the origins of things. Betelgeuse will do this.
it will send its processed material outward into the surrounding cloud. Some of it will drift for millions of years before it finds its way into a collapsing gas cloud and begins to form something new. The timeline is incomprehensible, but the chain of events is real, and it connects this moment, you, here, now, in the dark, to a star that will one day no longer be there.
In October of 2019, astronomers began to notice something unusual about Betelgeuse. The star was getting dimmer. This was not unprecedented. Betelgeuse is classified as a semi-regular variable star, meaning its brightness fluctuates on several overlapping cycles. One cycle runs approximately 420 days. Another runs about 5.5 to 6 years. Brightness changes are expected. They are normal. They are part of how the star behaves. But what happened between October 2019 and February 2020 was not normal variation. The star's visual magnitude dropped from around 0.5, making it one of the 10 brightest stars in the sky, to around 1.6.
By February 2020, it had dimmed by approximately 60%. For professional astronomers and amateur skywatchers alike, the change was visible to the naked eye. Betelgeuse, one of the most prominent stars in the night sky, had become noticeably, unmistakably fainter. The internet did what the internet does. Articles circulated. Videos were shared. The phrase, "Betelgeuse is about to go supernova," spread with the particular velocity of a story that is just frightening enough to be exciting and just plausible enough to feel credible. And to be honest, the scientific community did not immediately dismiss the speculation. The dimming was significant enough that serious papers were written considering whether this might be a precursor event.
Whether the star's surface was showing signs of the kind of extreme disruption that might precede a core collapse. The two main hypotheses that emerged were these. The first, a large, cool convective cell. A bubble of relatively cold plasma, much like a sunspot but on an enormous scale, had risen to the surface of the star and lowered the luminosity of a significant portion of its visible hemisphere. The second, the star had ejected a mass of material into the space immediately around it, and that material had condensed into dust, and the dust was blocking the light reaching Earth. In 2021, a team led by Miguel Montargé published research in the journal Nature that settled the question with unusual clarity.
Using the Very Large Telescope in Chile to resolve the surface of Betelgeuse directly. A feat possible for only a handful of stars, because Betelgeuse is large enough and close enough to show actual surface detail. They found that both processes had been happening simultaneously. A convective plume had erupted from the southern hemisphere of the star, ejecting a significant mass of material outward. That material had cooled rapidly in the outer atmosphere of the star and condensed into a cloud of silicate dust. The dust cloud, positioned between Earth and the southern hemisphere of Betelgeuse's surface, had blocked a large fraction of the star's light. The dimming was not a sign of imminent collapse. It was a sneeze.
An enormous stellar-scale sneeze, in which the star expelled a mass of material equivalent to several times the mass of our moon in the form of fine particulate dust, creating a temporary veil between itself and the eyes watching it. Betelgeuse recovered, By April 2020, the brightness had returned to typical levels. And then, in 2023, the star became unusually bright, brighter than its normal maximum, before settling again into its variable rhythm. The star continues to be monitored with intensity. It has earned the attention. But there is something worth sitting with in the story of the Great Dimming, as it has come to be called.
For approximately 4 months, the entire field of professional astronomy, along with millions of interested observers around the world, found themselves paying close attention to a single star, watching it, waiting, not knowing whether what they were seeing was mundane stellar physics or the beginning of an event that none of them would live to see resolved. A star changed its face, and the species looking up at it held its breath. That says something about the relationship between humans and the night sky. It is a relationship built on constancy. The stars are always there. They are always in the same positions. They are always the same brightness.
This is a fiction, of course. The stars are moving, they are changing. They will one day be different configurations. But the time scales of their changes are so long that within a human lifetime, and within recorded human history, the fiction is functionally true. The sky is stable. The sky is reliable. And then Betelgeuse gets dim, and suddenly the constancy is revealed to be an assumption. Not a law, not a guarantee. Just an assumption that happened to be correct for long enough that we forgot it was an assumption. The universe had not changed. The rules of stellar physics had not changed. Betelgeuse had simply done what large, volatile, evolved stars sometimes do.
But the feeling that many people reported, something between excitement and unease, something between wonder and a quiet, low-grade alarm. That feeling was real. It came from somewhere genuine. It came from the recognition that the familiar is not the same as the safe. The dust that dimmed the star was real material. It had mass and temperature and composition. It was made of tiny silicate particles, mineral compounds, similar in chemistry to the material that makes up rock and sand here on Earth. Those particles formed in the cooling outer atmosphere of a star 640 light years away, and then drifted slowly outward.
Some small fraction of that dust will eventually make its way, over millions and millions of years, into molecular clouds where new stars form. It will be incorporated into the raw material from which new solar systems condense. Some of it may end up in new planets. Some small number of those particles may end up in the atmospheres of worlds where something breathes. The sneeze that dimmed the star in 2019 is already on its way to becoming part of something else entirely. The universe recycles with perfect efficiency. Nothing is wasted. Everything eventually becomes something. The Great Dimming also taught astronomers something specific about how Betelgeuse loses mass.
A star this large and this evolved sheds material continuously. Its stellar wind carries millions of tons of gas per second into the surrounding space. But occasional events, like the convective eruption of 2019, shed mass in more sudden, more dramatic pulses. The ejected dust cloud was a concentrated burst of mass loss, equivalent to perhaps 2 to 4 times the mass of the Moon, released in a matter of months. Over the course of its 8 million-year life, Betelgeuse has lost somewhere between 3 and 5 solar masses of material this way, slowly, through wind, and occasionally through these larger episodic eruptions. The material surrounds the star in a series of nested shells, the accumulated record of the star's own history.
Astronomers can study those shells to learn about what the star was doing hundreds of thousands of years ago. The star writes its own biography in dust and sends it outward for anyone patient enough to read it.
When the iron core of a massive star collapses, the event that follows is the most energetic single occurrence in the observable universe, short of the Big Bang itself. That sentence contains more than it first appears to. The collapse takes less than a quarter of a second. The iron core, which has been accumulating slowly over thousands of years, approaching the Chandrasekhar limit, grain by grain in stellar terms, reaches the threshold and falls inward at speeds approaching 1/4 of the speed of light. The electrons and protons in the iron atoms are forced together under pressures so extreme that they merge to form neutrons.
The core transforms into a ball of neutronium, the size of a city but with the mass of 1.5 to 2 suns. The infalling outer layers strike this suddenly rigid core and rebound. The shockwave that results travels outward through the star at enormous speed, carrying with it an energy budget that is difficult to comprehend even approximately. In those first few seconds, the collapsing star releases more energy than our sun will emit over its entire 10 billion year lifetime. That energy exits the star primarily as neutrinos. Roughly 99% of the total energy released in a core collapse supernova is carried away by neutrinos, tiny, nearly massless particles that interact with almost nothing. They pass through the star. They pass through space.
They pass through the Earth. They pass through you. In 1987, a star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, roughly 168,000 light-years away, underwent core collapse. The supernova was visible to the naked eye from the southern hemisphere. It was the nearest supernova observable since the invention of the telescope. Several hours before the light arrived, before anyone had seen anything in the sky, neutrino detectors in Japan, in the United States, and in the Soviet Union registered a burst of neutrino events. 24 individual neutrino detections across the 3 facilities spread over a window of approximately 13 seconds. 24 events from 168,000 light-years away, through the entire bulk of the Earth.
The light, when it arrived hours later, confirmed what the neutrinos had already announced. A star had died. The death had sent its first messenger. The neutrino burst through essentially all matter without resistance. The light had taken longer, struggling through the outer layers of the dying star before finally escaping. This is a consistent feature of core collapse supernovae. The neutrinos come first, by hours. The light comes after. If Betelgeuse collapses, the neutrino detectors that humanity has built, Super Kamiokande in Japan, Ice Cube at the South Pole, others around the world, will register the event hours before any human eye sees anything change in Orion. There are automated alert systems in place. The detectors are watching.
If a sudden burst of neutrinos arrives from the direction of Betelgeuse, the alert will go out within minutes. The light, when it finally arrives, will be extraordinary. Astronomers estimate that Betelgeuse at peak supernova brightness would reach a visual magnitude somewhere between -7 and -12. For context,
The full moon has a visual magnitude of approximately -12.7. This means that Betelgeuse at supernova could approach the brightness of the full moon, not the star-like point of a bright star, but a diffuse extended glow, visible in full daylight, casting faint shadows at night. It would remain visible for weeks, possibly months.
The star that has been a quiet orange point in the shoulder of Orion your entire life would become a second light source in the sky. Every clear night, every clear day, that brightness would be there, and then it would fade. Slowly, over the course of months, it would dim back to something the naked eye could no longer see, and eventually, where Betelgeuse once was, there would be something new, an expanding cloud of superheated gas and dust, spreading outward at roughly 10% the speed of light, glowing in radio waves and X-rays, and eventually visible light as it slows and cools over the coming millennia. At the center of that expanding cloud, something would remain.
What that something is depends on the mass of the collapsed core. If the core settles at around 1.5 to 2 solar masses, the result is a neutron star, the most extreme form of matter that physics currently recognizes as possible. A neutron star is the size of a small city. Its surface temperature is in the hundreds of millions of degrees, and it can spin hundreds of times per second, sweeping beams of radio emission around with each rotation. These are pulsars. They are lighthouses in the debris of a stellar death.
If the core mass exceeds the upper limit for neutron star stability, roughly 2 to 3 solar masses, the exact number depending on still uncertain physics, then the collapse does not stop at neutron star density. It continues. The escape velocity exceeds the speed of light. Nothing gets out. What remains is a black hole, the most silent thing in the universe, something from which not even information escapes, born from the most energetic event short of the Big Bang. There is a particular quality to this transformation that is worth dwelling on.
The star that has been fusing elements for 8 million years, that has processed hydrogen into helium, helium into carbon, carbon into the heavier elements, all the way up the periodic table to iron. That star, in less than a second of clock time, vanishes as a star entirely. All that energy, all that light, all that material, and in its place, a city-sized ball of impossibly dense matter, or an absence in space-time that nothing can illuminate. The loudest thing in the galaxy produces either the quietest remnant possible, or no remnant at all.
And for the moment of the collapse itself, in those few seconds when the energy released exceeds the sun's entire output over billions of years, the star is, briefly, brighter than the 100 billion other stars of the Milky Way combined. One star, for a few seconds, outshining a galaxy. The star you have always known, the quiet orange point in the shoulder of Orion, is carrying this possibility inside it, not as a metaphor, as physics, as the literal future state of the iron core currently sitting at its center, growing slowly toward the mass that will end it.
Everything that the word supernova contains, the collapse, the rebound, the neutrino flood, the light, the remnant, all of it is the eventual fate of the star you can see on any clear winter night, with nothing but your eyes and a dark sky. It is simply a matter of time, and time, at the scale of stars, is not something that accommodates urgency or reassurance.
It moves on its own terms. It does not respond to the fact that 640 light-years away, a small planet has developed creatures who have learned to look up and ask questions. The questions are excellent. The universe has no comment. There is one more dimension to the supernova that deserves attention before we move forward.
The Crab Nebula, in the constellation Taurus, is the remnant of a supernova that Chinese astronomers recorded in the year 1054. At the time of its explosion, the star was roughly 6,500 light-years away, 10 times farther than Betelgeuse. Records from that era describe it as visible in daylight for 23 days. It was bright enough to be seen at midday. It was 4 times brighter than Venus. For nearly 2 years, it remained visible to the naked eye at night. That was from 10 times the distance. Betelgeuse, if it explodes, is at 1/10 of that distance.
The inverse square law of light propagation means that for the same absolute brightness, the apparent brightness from Earth would be 100 times greater at 1/10 the distance. Even accounting for the fact that the two stars are different sizes and will produce different total energy outputs, the Betelgeuse supernova will almost certainly be a far more dramatic event than the one that produced the Crab Nebula, one of the most historically documented astronomical events in recorded history. There will be no missing it. The question is not whether Betelgeuse will explode. It is what that explosion will do to the third planet from a star called the Sun.
The question is not whether Betelgeuse will explode. It is what that explosion will do to the third planet from a star called the Sun. When a star the size of Betelgeuse collapses, it does not simply go dark. It releases more energy in 10 seconds than our Sun will produce across its entire 10-billion-year life. Let that settle for a moment. 10 seconds. 10 billion years. Those two intervals are placed in the same sentence, as though they belong together. They do not. There is no frame in which those timescales are comparable, and yet the physics of stellar death makes them equivalent in terms of energy output. The total energy released in a core collapse supernova is approximately 3 × 10 to the power of 46 joules.
That number does not communicate. It is too large. It passes through understanding without leaving a mark. Try it this way. The Sun in 1 second releases approximately 4 × 10 to the 26th joules. That is already a number too large to feel. But if you took the Sun's total lifetime output, all 10 billion years of it, and compressed it into a single moment, you would be approaching the energy of a single core collapse supernova. Not a fraction of it, the entirety of it.
If you took every nuclear weapon ever designed, built, tested, or deployed by every nation in human history, thousands of warheads, from the smallest tactical device to the largest thermonuclear bomb ever detonated, and set them all off simultaneously, the total energy would not register as a rounding error against what Betelgeuse will release when its core gives way. The comparison is not dramatic, it is arithmetic. The supernova wins by a factor of roughly 10 to the 28th, or think of it this way. The largest nuclear weapon ever detonated, the Soviet Tsar Bomba, in 1961, released energy equivalent to approximately 50 megatons of TNT.
That blast scorched the atmosphere across hundreds of kilometers, shattered windows 1,200 kilometers away, and was detected by seismographs on the other side of the planet. A Betelgeuse supernova, at its peak optical luminosity alone, just the visible light, just the 1% that isn't neutrinos, outshines the jar bomba by a factor more than 1 trillion times over. The weapon we built that frightened us most, the one that redefined what it meant to talk about destruction, is a candle flame next to what stars do routinely at the ends of their lives. But here is what the physics actually tells us, and what makes this event stranger than the raw numbers suggest.
99% of that energy, nearly all of it, will leave as neutrinos. Particles so weakly interacting that they pass through the entire planet as though the planet were fog. The light, the spectacle, the blinding optical glory that will make Betelgeuse visible in broad daylight for weeks on end. That brilliant performance represents less than 1% of the total energy being released. What we will see is the afterthought. The main event is invisible. It passes through us and is gone before the star has even finished collapsing. The 1% that remains, still an almost incomprehensible figure in absolute terms, is distributed across a range of electromagnetic wavelengths. Optical light, ultraviolet, X-rays, gamma rays.
At peak brightness, the supernova is estimated to reach somewhere between -7 and -12 on the magnitude scale used by astronomers. Magnitude is a logarithmic scale, and it runs backwards. More negative means brighter. The full moon sits at approximately -12.7. Venus at its brightest reaches roughly -4.9. Betelgeuse, at the extreme of current estimates, might challenge the full moon in luminosity. A star becoming as bright as the moon, in a fixed point in the sky, in a familiar constellation, casting shadows at night, visible as a distinct object at noon. This will last for weeks, possibly months, at diminishing intensity. The peak will be brief, days, not months. Then the light will fade, but slowly.
The supernova will remain a naked-eye object for perhaps a year. It will remain visible in small telescopes for longer. We have a template. Supernova 1987A, in the Large Magellanic Cloud, peaked at approximately +2.9 magnitude, visible to the naked eye from the southern hemisphere, but unremarkable to casual observers. It faded over the course of a year. Betelgeuse, at perhaps 100 times closer, will be approximately 10,000 times brighter at peak. But gamma rays and X-rays, the forms of radiation that do not merely dazzle but damage, also stream outward. The good news is physics, specifically the inverse square law. Radiation intensity falls with the square of distance. Double the distance, reduce the intensity by a factor of 4.
10 times the distance, 1/100th the intensity. Betelgeuse sits somewhere between 550 and 900 light-years away. The current best estimate, derived from Hipparcos satellite data and more recent parallax measurements, centers on approximately 700 light-years. 700 light-years. That is approximately 6.6 quadrillion kilometers. At that distance, Even the gamma-ray flux from the explosion will be spread so thin by the time it reaches us that it represents no measurable threat to life on Earth's surface. The threshold for real danger, the distance within which a core collapse supernova could plausibly cause mass extinction through radiation, is estimated at roughly 25 to 50 light-years. Some models tighten that range, some expand it slightly.
But the rough consensus holds that within 50 light-years, the ozone depletion from gamma radiation would be severe enough to fundamentally alter the biosphere. At 700 light-years, we are at least 14 times beyond even the outer edge of that danger zone. The gamma rays that strike our atmosphere will be absorbed or scattered high in the stratosphere. A small fraction will reach the surface. The dose will be detectable with instruments. It will not be detectable by the human body. There may be a minor transient effect on the ozone layer. Some estimates suggest a reduction of no more than a few % in the months following the event, as the high-energy radiation interacts with oxygen and nitrogen in the upper atmosphere. This would be a blip.
Smaller in effect than a major volcanic eruption. Temporary. The ozone reduction from a Betelgeuse supernova, by most current estimates, would be roughly 1 to 3% globally over the course of months following the event. The Mount Pinatubo volcanic eruption of 1991 reduced global ozone by a comparable margin through a completely different chemical mechanism, and the layer recovered within a few years. Betelgeuse will not end the ozone layer. Betelgeuse will not meaningfully increase cancer rates. Betelgeuse will not sterilize the land or poison the oceans. This bears repeating because the mind, when confronted with the scale of what a supernova is, tends to assume the consequences must match the spectacle. They do not.
The universe can produce an event of almost incomprehensible violence and have it register on the surface of a living planet as a slightly elevated ultraviolet reading for a season. We are safe. At this distance, we are thoroughly, conclusively, almost boringly safe from the physical radiation of the explosion. Life on Earth will not end. Life on Earth will barely notice in biological terms. And yet there is something that the numbers, for all their reassurance, cannot quite put to rest. The explosion itself is not calibrated to our safety. It is not reduced in any way because we are watching. It is not diminished because living things exist nearby by cosmic standards.
It is the gap between us and something that at closer range would sterilize a planet. Distance is not safety. Distance is luck. We are lucky. We have always been lucky. We will need to stay lucky for as long as we want to continue existing. That is not a comfortable thought to fall asleep to. But it is an honest one. The universe does not hate us. It does not love us. It does not arrange itself around our survival. It simply operates. And so far, the distances have been sufficient. So far.
The light from the supernova will not arrive first. Something else will come before it. Something invisible. Something that will pass through the planet entirely unobstructed. Something you will not be able to detect with your body or your senses or any device you carry. The neutrinos will arrive hours ahead of the light. To understand why, you have to understand what happens in the first second of a core collapse supernova. When the iron core of a massive star
can no longer sustain fusion. Iron is the end of the line, the point where fusing nuclei absorbs more energy than it releases. The core begins to collapse under gravity.
It takes approximately 1/4 of a second to fall from a sphere, roughly the size of Earth, to a sphere approximately 20 kilometers across. The density at the center of that collapsed core exceeds the density of an atomic nucleus. Matter becomes so compressed that individual protons and electrons are forced together, producing neutrons and releasing neutrinos in enormous quantities. Within the first second, the collapsing core generates roughly 3 × 10 to the 53rd joules of energy in neutrinos alone. And those neutrinos leave almost immediately. The outer layers of the star, the hydrogen envelope, the helium layer, the carbon and oxygen shells above the collapsing core, do not yet know what has happened.
The information about the collapse travels outward as a shockwave at a fraction of the speed of light. It takes time. The outer star takes several hours to respond, but the neutrinos produced in the collapsing core barely interact with even the dense interior of a dying star. They stream outward. They are already in interstellar space before the shockwave has made it through the stellar interior. They travel at velocities extremely close to the speed of light. They arrive at Earth 1 to 3 hours before the expanding shockwave has torn through the stellar envelope and allowed the first photons to escape. We know this because it has happened once in our recorded astronomical history.
On the 23rd of February, 1987, a blue supergiant star called Sanjulik -69°202 exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, approximately 168,000 light-years from Earth. We call the event Supernova 1987A. Hours before any telescope on Earth registered a change in that region of the sky, 3 neutrino observatories independently detected anomalous bursts of particles. The Kameokande II detector in Japan recorded 11 events. The IMB detector in Ohio recorded 8. The Baksan Neutrino Observatory in the Soviet Union recorded 5. 24 neutrinos total. 24 particles out of approximately 10 to the 58th. Astronomers had predicted that the neutrino burst should arrive before the light.
The theory had been there, waiting on paper for years. And then, in a single night, from 3 independent underground detectors on different continents, the prediction was confirmed. This is one of the cleanest experimental confirmations in the history of astrophysics. A prediction made from theory, verified in real time by instruments no one had built specifically to catch that event. The detectors existed. The star cooperated. The universe delivered. The numbers require some accounting. The supernova released approximately 10 to the 58th neutrinos in total, radiating in all directions. Of those, the fraction that passed through Earth, a small disk, a target at a distance of 168,000 light-years, was a tiny proportion.
And of those, only 24 struck a nucleus in a detector and produced a detectable signal. The rest passed through the planet without incident, through the rock, through the water, through everyone sleeping in the southern hemisphere at the moment the burst arrived. Now consider Betelgeuse. 168,000 light-years versus 700 light-years. The intensity of radiation falls with the square of distance. Betelgeuse is approximately 240 times closer than the source of supernova 1987A. The neutrino flux at Earth from a Betelgeuse supernova will be roughly 57,000 times greater than what 1987A produced.
Where 1987A sent 24 detectable events through the then current generation of detectors, the Betelgeuse supernova is expected to produce thousands of interactions in Super Kamiokande alone in the first seconds. Super Kamiokande is the successor to Kamiokande II. It holds 50,000 metric tons of ultra-pure water, contained in a cylindrical tank buried beneath a mountain in Japan, watched over by approximately 13,000 photomultiplier tubes. Those tubes detect Cherenkov radiation, a faint blue glow, like a sonic boom but for light, produced when a high-energy particle travels through water faster than light travels through water. It is the signature of a particle interaction. Most of the time, those tubes detect background, cosmic ray muons, radioactive decays, random noise.
The detectors are buried under mountains specifically to screen out as much of this as possible. When Betelgeuse collapses, the background will be overwhelmed. Ice cube is a different kind of detector. A cubic kilometer of Antarctic ice, at a depth between 1.4 and 2.4 kilometers beneath the South Pole, threaded with 5,160 digital optical modules watching the ice for the same Cherenkov signature. IceCube is designed primarily for very high-energy neutrinos from distant astrophysical sources. For a nearby supernova like Betelgeuse, it will detect not individual interactions, but a global rise in the noise baseline across all modules simultaneously, a statistical burst above background.
In the seconds after core collapse, IceCube is expected to register hundreds of thousands of excess counts. The Supernova Early Warning System, SNOOZE, links these and other neutrino detectors worldwide. When multiple detectors register a coincident burst within a short window, an automated alert fires. It goes to astronomers. It goes to observatories. It says, simply, something is about to happen in the direction of the sky we have been watching. Point your instruments there. You have 1 to 3 hours. Think about what those hours would be like. It would be the middle of some ordinary night. Someone would be asleep. Someone else would be checking instruments in a control room, half attentive. A monitor would change. A threshold would be crossed.
Within seconds, the automated cross-check would come back positive from another observatory on the other side of the planet, and then another. The snooze alert would go out, phones would ring, telescopes would slew, the enormous mechanically precise rotation of mirrors that have spent their whole operational lives pointing at different questions in the dark, and they would all point toward the same place, the shoulder of Orion. And for an hour, perhaps 2, nothing visible would change. The star would still look like Betelgeuse, a familiar orange, slightly variable point of light.
But already, the neutrinos would be spreading outward through the solar system, through the space between planets, through the upper atmosphere, through the rooftops of cities and the sleeping bodies of billions of people who know nothing yet. Every square centimeter of every living thing on the planet facing the direction of Betelgeuse would be traversed by roughly 10 billion neutrinos per second during that burst. Your body, at that moment, would be interpenetrated by the signature of a stellar death, and you would feel nothing. Not because nothing is happening, but because you are made of the wrong kind of matter to interact with neutrinos on any scale that registers biologically. Neutrinos interact through the weak nuclear force.
The weak force is, in practical terms, extraordinarily reluctant to engage with matter. A neutrino could travel through a column of solid lead stretching from here to the nearest star and have roughly even odds of interacting with a single atom. You are not dense enough. You are not vast enough. You are, in neutrino terms, completely transparent. The neutrinos from the death of a star will pass through you, through the planet, through the sun on the other side, and continue outward into intergalactic space, carrying their information, their record of the event, long after all of us are gone. They are a kind of memorial, undetectable to the things they pass through, carrying the news of something that no longer exists.
There is a strange kind of intimacy in that. The most violent moment in the life of a star, the instant of core collapse, the birth of a neutron star or black hole, the moment when something larger than 1 billion Earths becomes something 20 kilometers across, will pass through you, and you will not know. You will be asleep, or you will be making coffee, or you will be in the middle of a conversation about something entirely ordinary, and the universe, at that moment, will be writing something enormous across your body in a language your body cannot read. This is what it means to be human-sized in a universe that operates at scales we can measure but cannot feel. We built the detectors to compensate.
To extend our perception into a range our biology cannot reach. 100,000 tons of pure water, buried in a mountain in Japan, serves as a kind of prosthetic sense organ, a way to feel what the universe is doing in realms where the body is useless. We built it for moments like the death of Betelgeuse. We built it knowing it might wait 100,000 years.
There is a more unsettling possibility. Not a certainty, probably not even a significant probability, but it exists in the calculations, and it has existed in the geological record, and so it belongs in this conversation. Some core collapse supernovae do more than explode symmetrically outward. Some of them, the ones involving the right combination of stellar mass, rotation rate, and magnetic field, launch jets, collimated beams of plasma accelerated to relativistic velocities along the rotational axis of the collapsing star. These jets punch through the stellar envelope, drilling outward along the poles of the dying star, and emerge as beams of energy so intense they can be detected across billions of light years. We call these events gamma-ray bursts.
Long-duration gamma-ray bursts, lasting anywhere from a few seconds to several minutes, are associated with the collapse of rapidly rotating massive stars. They are the most energetic electromagnetic events in the observable universe. A single burst can briefly outshine an entire galaxy in gamma rays. In the early decades of gamma-ray burst research, before their extragalactic nature was established, astronomers debated what could possibly produce such events. The energy requirements seemed impossible. The answer was a dying star under the right conditions. The mechanism involves the angular momentum of the collapsing core. If the core is rotating rapidly enough, the infalling material forms an accretion disk around the newly forming compact object at the center. Magnetic fields become enormously amplified.
Energy is extracted from the rotation
and launched outward along the magnetic poles in narrow relativistic beams. These beams are extremely narrow, perhaps a few degrees of opening angle. They are not omnidirectional explosions. They are more like cosmic searchlights sweeping a small fraction of the sky, which means that even if a star near us produces a gamma-ray burst, the question of whether Earth is in the beam matters enormously. If the beam is aimed at us, and the source is within a few thousand light-years, the consequences are severe. The gamma rays strike the upper atmosphere. They dissociate nitrogen and oxygen molecules. This produces nitric oxide and other nitrogen oxides, which are extraordinarily efficient catalysts for ozone destruction.
The ozone layer, the thin stratum of triatomic oxygen molecules between roughly 15 and 35 kilometers altitude that shields the surface from the most damaging ultraviolet wavelengths, would be chemically dismantled. Estimates suggest a gamma-ray burst from within a few thousand light-years, aimed directly at Earth, could reduce ozone concentrations by 25 to 50% globally. Recovery would take years, during which ultraviolet radiation at the surface would increase dramatically. The consequences at the surface would be severe. DNA absorbs ultraviolet radiation efficiently. At sufficiently high doses, the damage to living tissue accumulates faster than it can be repaired. Phytoplankton. The microscopic photosynthetic organisms that form the base of the marine food chain and produce roughly half of Earth's oxygen are particularly sensitive to ultraviolet exposure.
If phytoplankton populations collapsed, the marine food chain would unravel from the bottom. Species after species would lose their food supply. The cascade would move upward through the food web. On land, organisms accustomed to current ultraviolet levels would find themselves in an environment their biology was not built for. Agricultural crops, many of which have been selectively bred for productivity rather than stress tolerance, would be vulnerable. The ozone layer is not a robust shield. It is a thin chemical equilibrium, a balance between creation and destruction of triatomic oxygen, sustained by the specific energy budget of ultraviolet light reaching the stratosphere. This balance has been disrupted before by human-made chlorofluorocarbons. It was disrupted by the Pinatubo eruption.
It would be disrupted, drastically and suddenly, by the nitrogen oxide pulse from a nearby gamma-ray burst. The difference is scale and speed. The Montreal Protocol gave us time to respond to ozone depletion from CFCs. A gamma-ray burst gives no warning and no remedy. The chemistry happens in minutes. The ozone disappears in months. The ultraviolet comes in before anything can be done about it. Now, does Betelgeuse produce a gamma-ray burst when it explodes? Probably not. The prevailing models suggest that long-duration gamma-ray bursts require rapidly rotating progenitor stars. The angular momentum of the collapsing core needs to be high enough to form a stable accretion disk and drive a jet. Betelgeuse, in its current red supergiant phase, is thought to be a slow rotator.
Its surface rotation velocity is estimated at several kilometers per second, modest for a star of its size. As a red supergiant, it has expanded enormously and shed angular momentum in the process. Without sufficient angular momentum in the core, a relativistic jet is unlikely to form and sustain itself long enough to punch through the stellar envelope. Most models place Betelgeuse in the category of stars likely to produce a standard core collapse supernova, spectacular, but not a gamma-ray burst. And even if Betelgeuse did produce jets, the second question would be orientation. The rotational axis of Betelgeuse, the axis around which the star spins, and along which any jets would emerge, has been estimated from observations of surface features and the surrounding circumstellar material.
Studies, including work by Uitenbroek and colleagues in the 1990s,
have suggested the rotational pole is inclined by approximately 20 degrees relative to our line of sight. A gamma-ray burst jet from Betelgeuse, if one formed, would likely miss Earth by a significant margin. Likely. That word is doing real work in that sentence. The uncertainty matters because the observations are difficult. Resolving the surface and orientation of a star 650 light-years away is at the frontier of what current telescopes can do. The error bars are not trivial, and stellar rotation is not perfectly rigid. Different layers of a massive star can rotate at different rates.
The deep interior, the part that collapses, the part that matters for jet formation, may have different angular momentum than the surface we observe. We do not have direct measurement of Betelgeuse's core rotation. What we have is inference. Careful, evidence-based inference. But inference nonetheless. And so the gamma-ray burst question for Betelgeuse is probably not, and probably not aimed at us. Two layers of reassurance, each with their own uncertainties. That is the honest state of knowledge. But now consider the deep past. 445 million years ago, a mass extinction event unfolded on Earth. We call it the end, Ordovician extinction. The Ordovician extinction.
Reefs, trilobites, brachiopods, graptolites. The oceans were full of life in forms we would barely recognize. Then, over a period of roughly 2 million years, brief by geological standards, approximately 85% of marine species disappeared. It was one of the 5 great extinctions in the history of complex animal life. The primary explanation is glaciation. The supercontinent Gondwana drifted over the South Pole, triggering global cooling. Sea levels dropped dramatically as water locked into ice sheets. Shallow marine habitats, where most Ordovician life existed, were devastated. But some researchers noticed a pattern in the extinction that the glaciation hypothesis struggled to fully account for. The organisms that survived, and those that did not, showed a spatial bias.
Deeper water species were disproportionately likely to survive compared to shallow water and nearshore species. This is consistent with glaciation. Shallow water cools faster, and sea level drops expose shallow habitats. But it is also consistent with elevated ultraviolet radiation at the surface. Organisms deeper in the water column would be partially shielded. Those living in shallow, well-lit water would be most exposed. In 2004, astrophysicist Adrian Melat and colleagues published a paper proposing that a gamma-ray burst, originating from a source within a few thousand light-years of Earth, aimed approximately in our direction, could have contributed to the end Ordovician extinction. The burst would have depleted the ozone layer. Ultraviolet radiation would have increased at the surface. Marine photosynthetic organisms near the surface, the base of the food chain, would have suffered. The cascade would have followed. The hypothesis received serious attention. It was not dismissed. It was also not confirmed. The fundamental difficulty is that gamma-ray bursts leave no direct geological signature we can currently identify. They do not produce a chemical anomaly in sedimentary layers the way an asteroid impact leaves iridium. They do not create characteristic debris the way a large volcanic eruption creates ash layers. What a gamma-ray burst leaves behind is an absence, a gap in the ozone layer, an increase in ultraviolet damage to organic molecules, a disruption to food webs.
These signals are real, but they are indirect, and they overlap with signals that glaciation can also produce. The consensus in paleontology remains that glaciation is the primary driver of the end Ordovician extinction. The gamma-ray burst hypothesis is a supplement, a possible contributing factor that cannot be ruled out. Cannot be ruled out. That phrase in science carries a specific weight. It does not mean probable. It does not mean likely. It means the evidence does not yet exclude the possibility. And the possibility is this: something burning in the galaxy 445 million years ago may have peeled back the roof of our sky for a brief and terrible interval. Ultraviolet light poured in. The food chains unraveled. Most things died.
The survivors, the species that were deep enough, or shielded enough, or simply different enough to tolerate what the sky had become, rebuilt over millions of years. Hundreds of millions of years later, their descendants built cities and telescopes and neutrino detectors. We may owe our existence, in part, to the geometry of a long-dead star's rotation. The axis tilted in the wrong direction. The beam swept somewhere else. Something lived that might otherwise have died. Evolution continued. We arrived. There is a version of this story in which 1 degree of arc is the difference between a world with philosophy and a world with no vertebrates. 1 degree. The angle at which a dying star happened to be spinning when it exploded. We call that survival.
We call ourselves the dominant species on the planet. We call ourselves conscious. And beneath all of that, beneath all the names we give ourselves and all the significance we attach to our existence, we are organisms that happen to be alive because the angle was sufficient. The sky in other times and in other places has been aimed differently. In those places, no one is here to think about it. And perhaps that is the deepest strangeness in all of this. Not that the universe is dangerous, not that stars explode, not that jets of plasma travel at relativistic velocities and strip the roofs off planetary atmospheres without warning or intent. The deepest strangeness is that any of this is being thought about at all.
That organisms which arose from the wreckage of ancient extinctions, which evolved on a planet that has been scorched and frozen and cratered and flooded across billions of years, have arrived at a point where they can reconstruct the mechanism of their own near misses. We look at the Ordovician fossil record and we can infer the shape of the sky over those ancient seas. We can argue about whether a long dead star's beam is written into the gaps in the fossil record. We can do this 445 million years after the fact. That capacity to reach backward through time across scales that dwarf our own existence and reconstruct events in which no mind was present is one of the stranger things evolution has produced.
We are the universe becoming aware of what it has done to itself, and what it has done and continues to do is indifferent, violent, beautiful, enormously, far beyond any scale of meaning that organisms like us can naturally hold. The gamma-ray burst question for Betelgeuse has a practical answer. Probably not, and probably not aimed at us. But the question underneath the question, whether the sky has killed before, and whether it will kill again, and whether we are in a momentary calm between events, has a different kind of answer. Yes. Yes to all of it. We are in the calm. The calm has lasted long enough to produce us. We would prefer it to continue. There are telescopes pointed at Betelgeuse right now. Not occasionally. Not when something interesting happens. Continuously. In the Chilean Atacama Desert, one of the driest places on Earth, the Very Large Telescope consists of 4 main instruments, each with a primary mirror 8.2 meters across. Through interferometry, a technique that combines the light from multiple mirrors as though they were a single, larger instrument, it achieves a resolution that can resolve details on the surfaces of the nearest giant stars. Betelgeuse is one of those stars. The angular size of Betelgeuse in our sky is approximately 55 milliarcseconds. 1 milliarcsecond is 1,000th of 1 arcsecond. 1 arcsecond is 1/3000th, 600th of 1 degree.
To resolve a disk 55 milliarcseconds across is to see a star's surface. Not infer it, not model it, actually see it. In 2017, the gravity instrument on the Very Large Telescope interferometer produced images showing the bright, asymmetric surface of Betelgeuse directly. Bright spots, regions of elevated temperature driven by enormous convective upwellings, were visible as distinct features on the stellar disk. In 2021, a team led by Miguel Montargé published images in Nature that showed what had actually happened during the Great Dimming. The southern hemisphere of the star appeared darkened, not because the star was dying, but because a large convective cell had erupted from beneath the surface and ejected material outward.
That material, as it expanded and cooled in the space above the photosphere, condensed into dust. The dust cloud obscured the southern hemisphere as seen from Earth. The star did not dim because it was failing. It dimmed because it sneezed. A convective eruption, a bubble of hot plasma rising from the deep interior, breaking the surface and ejecting material into the circumstellar environment, caused the apparent brightness drop that briefly convinced portions of the internet that human civilization was about to be reconfigured by stellar violence. It was not. But the episode illustrated something important about what it means to watch a star this closely. We can see individual surface features. We can track their evolution.
We can, in principle, distinguish between a transient convective event and something more permanent, the kind of structural change in the outer layers that might precede the final collapse. ALMA, the Atacama Large Millimeter Array, contributes a different kind of observation. Millimeter and submillimeter wavelengths penetrate differently than visible light. They probe the chromosphere, the layer above the visible surface, and the extended outer atmosphere. ALMA has measured temperature gradients in Betelgeuse's chromosphere, mapped the distribution of molecules and atoms in the extended gas surrounding the star, and tracked changes in the circumstellar environment over time. The star is shedding material continuously. Mass loss through stellar winds is a standard feature of red supergiant life.
Betelgeuse loses roughly 1/10 millionth of a solar mass per year, a rate that seems small, but accumulated over millions of years, has built up a substantial cocoon of gas and dust around the star. When the supernova shockwave eventually tears through the stellar envelope and expands outward, it will crash into this material. The interaction will produce additional radiation. It will light up the immediate environment around the explosion in ways that depend on the detailed structure of what was shed and when. The Hubble Space Telescope has contributed ultraviolet observations. Wavelengths blocked by Earth's atmosphere and only accessible from space. Ultraviolet emission traces the hottest material, the most energetic processes in the outer atmosphere.
In 2020, Hubble observations revealed that the material ejected during the Great Dimming was moving outward at higher velocities than expected, suggesting a more energetic surface eruption than initially modeled. Every observation adds to a picture, a detailed, time-resolved portrait of a star in the final stages of its life. But the portrait has a fundamental limitation. We can see the surface. We can probe the outer atmosphere. We cannot see the core. The core of Betelgeuse is what determines everything. The rate of nuclear burning in the iron core region, the exact composition of the innermost shells, the precise mass of the iron core relative to the Chandrasekhar limit, the threshold beyond which electron degeneracy pressure can no longer prevent gravitational collapse.
When the iron core reaches that limit, approximately 1.4 times the mass of our Sun, collapse becomes inevitable. And it happens in less time than it takes to blink. The question we cannot yet answer from the outside is, how close is Betelgeuse's core to that limit right now? Models place Betelgeuse in the red supergiant phase. A phase that in stellar evolution terms is brief, measured in tens of thousands of years rather than millions. It is likely in the late stages of oxygen, burning in its core, or possibly neon burning. The core burning stages in a massive star accelerate dramatically toward the end. Hydrogen burning takes millions of years. Helium burning takes hundreds of thousands. Carbon burning, tens of thousands.
Neon burning, roughly a year. Oxygen burning, roughly 6 months to a year. Silicon burning, the last stage before iron, takes about a day. If Betelgeuse is currently burning oxygen in its core, the remaining time before collapse could be anywhere from a few years to 100,000 years. If it has already reached silicon burning, the timescale is months. We do not know which stage it is in. The surface gives only indirect clues. The core is hidden behind hundreds of millions of kilometers of stellar material. There is one way to know in advance.
Not to supernova levels, but to rates significantly elevated above baseline. Current detectors cannot catch this pre-collapse signal from 700 light-years away. The steady-state neutrino emission from a massive star's core is too dim at that distance. But proposed next-generation detectors, Hyper Kamiokande, a planned upgrade of Super Kamiokande with roughly 10 times the detection volume, might be able to see this pre-collapse signal from nearby massive stars. If those detectors are built and operational before Betelgeuse collapses, we might get days of warning rather than hours. But for now, the warning is 1 to 3 hours. When it comes, it will come as a number on a screen in an underground laboratory. The number will cross a threshold. An algorithm will compare it to readings from other detectors.
A confirmation will arrive, and then telescopes around the world will slew toward the shoulder of Orion. The night side of the planet will see a star that is not yet doing anything unusual. And then, over the course of an hour or two, It will begin. The brightening will be subtle at first, a few tenths of a magnitude, the kind of change Betelgeuse makes all the time in its ordinary variability. But this time, it will not stop. It will accelerate, over hours, then over days, until the shoulder of Orion is no longer a familiar orange point, until it is something bright enough to cast a faint shadow, until the most recognizable constellation in the northern sky is no longer what it was.
The people who see it first will be astronomers, awake in observatories, already prepared, the neutrino alert already on their screens. The rest of the world will wake up the next morning. They will look out their windows or step outside to check the weather or glance up without any particular intention, and they will see something that does not belong. A second object of roughly lunar brightness in the shoulder of Orion, where there should only be a star. There is no historical comparison for this in the modern era. The supernova of 1604, Kepler's star, briefly reached -2.5 magnitude, visible in daylight for 3 weeks, observed carefully by Johannes Kepler and by Galileo, who was then in his late 30s.
It contributed to the erosion of the Aristotelian cosmology, the idea that the celestial sphere was perfect, unchanging, beyond the reach of terrestrial decay. The supernova of 1572, Tycho's star, was studied obsessively by Tycho Brahe, who measured its position carefully enough to demonstrate it showed no measurable parallax. It could not be a nearby atmospheric phenomenon. It was among the stars. The stars, therefore, could change. Both of those historical supernovae were in the Milky Way, but in distant, unfamiliar regions of the sky. They were strangers that arrived unexpectedly. Betelgeuse is not a stranger.
Its orange color is familiar. Its position in Orion is memorized by children. When Betelgeuse explodes, it will not be a new object appearing in an unfamiliar part of the sky. It will be the destruction of something familiar, something that was there, something that was always there, something that for the first time is not. That is a different kind of loss. Each of these historical events cracks something in the prevailing cosmological certainty. The Betelgeuse supernova will not do the same kind of epistemic damage. We already know stars die. We already know the sky is not permanent, but it will do something else. It will make the abstraction real.
Every person who has ever learned that stars eventually explode has learned it as a piece of information, a fact that passes through the mind and is filed away among other facts. The Betelgeuse supernova will make it something that happened, something that is happening, something you can look at with your own eyes without any special equipment on an ordinary night in the constellation you have known since childhood. That shift, from abstract knowledge to witnessed event, is something language struggles to prepare you for. We have been building toward this moment for 400 years. The telescopes, the detectors, the models, the decades of careful observation, the satellite parallax measurements trying to pin down the exact distance, the surface imaging campaigns, the spectral monitoring.
The neutrino alerts,
all of it aimed at one question. What is Betelgeuse going to do, and what will it mean when it does it? And still we do not know when. It could be tonight. It could be 100,000 years from now. The instruments are watching. The detectors are waiting. The alerts are configured. We are as prepared as any civilization has ever been for a cosmic event of this kind. And we will still be surprised, not because of inadequate preparation, but because of the nature of anticipation. No matter how long you have been waiting, no matter how certain you are that it will eventually happen, the moment it actually does, happens without announcement. The moment the threshold is crossed, is not labeled in advance.
It simply arrives, and everything that was familiar becomes, in an instant, something else. Consider what the night sky has meant to every human generation before this one. For the overwhelming majority of human history, the stars were fixed. They moved with the seasons. They provided navigation. They anchored myth and calendar and religion. But they did not change. Not on timescales any human would live to observe. The sky was the one constant. Everything else, dynasties, climates, coastlines, languages, changed. The stars did not. We now know this is an illusion. The apparent permanence of the stars is simply the gap between stellar timescales and human timescales. Stars change constantly. They age, they pulse.
The sky is not a fixed backdrop. It is a slow catastrophe that moves too slowly for a human lifetime to witness, until it does not. The generation that watches Betelgeuse explode will be the generation that sees, for the first time in centuries, the sky change in real time. Not a planet moving along its path, not a comet appearing and fading, not a meteor burning up in the atmosphere. A star, a permanent, named, culturally embedded star, becoming, abruptly, something different. The sky will be rewritten, and the instruments we built, the detectors buried under mountains and frozen into continental ice, will have told us it was coming, just barely in time to watch.
We have pointed every instrument we have at it, and yet, when it happens, it will still catch us by surprise.
We have pointed every instrument we have at it, and yet, when it happens, it will still catch us by surprise. Think about what that means. Right now, at this moment, you may be looking at a star that no longer exists. The light reaching your eye tonight left Betelgeuse approximately 700 years ago. It has been traveling across empty space ever since, through the dark, through nothing, and only now, only at this precise second, does it finally arrive at the back of your eye. 700 years ago, in the year 1300 and something, the Black Death was spreading across Europe. Dante Alighieri was still alive. The Aztec Empire had not yet been founded.
And somewhere out there, around 700 light years away, Betelgeuse was doing exactly what it was doing when you last looked at it. Or perhaps it wasn't. There is a version of events in which Betelgeuse already exploded, not 700 years ago. Last week? Last year? A century ago. We would have no way of knowing. The explosion would have happened. The light would have begun its journey. And somewhere between here and there, it is still traveling, still approaching, still not yet arrived. This is one of the strangest things about living in a universe where light has a speed. The sky we see is not the sky that exists.
It is a collection of messages from the past, arriving at different delays, all composited into a single image our brains interpret as now. The moon you see is 1¼ seconds old. The sun is 8 minutes old. The stars in Orion range from a few hundred to a few thousand years old. When you look up at the night sky, you are not looking at one moment in time. You are looking at thousands of different moments, layered on top of each other, all presenting themselves to you, simultaneously, as though they belong together. They do not belong together. Not really. Betelgeuse sits at a distance that astronomers have struggled to measure precisely.
For decades, the accepted figure hovered around 700 light-years, but more recent estimates have placed it closer. Perhaps 550, perhaps as far as 900. The uncertainty matters not only for the physics, but for the strangeness. If the true distance is 550 light-years, then the light we see tonight left during the early 1400s. If it is 900 light-years, then the light left during the 1200s, when the Mongol Empire was still expanding across Asia. 700 years of human history passed while that light was in transit. Empires rose and fell. Languages were born and died. Entire civilizations assembled themselves and collapsed. And the photons carrying this particular piece of information just kept moving, indifferent, patient.
Crossing the interstellar void at 299,792,458 meters per second, without slowing, without stopping, without any awareness of the centuries accumulating behind them. If the explosion has already happened, then tonight, somewhere out there in the dark, a wall of light is rushing toward us. A shock front of photons, neutrinos, and radiation, expanding outward from the point where Betelgeuse used to be. That wall of light does not know we are here. It does not know anyone is here. It is simply expanding, as explosions expand, filling an ever larger sphere of space with the news of what happened.
One night, Orion will look exactly as it always has. And the next night, or the next week, or the next decade, a new light will appear in that constellation, not gradually, not with any announcement, just there, suddenly, where it wasn't before. Between the past and the present, there is a gap 700 years wide, and inside that gap is everything we do not know. The universe is full of silences like this, information traveling at the fastest possible speed, and still not fast enough to tell us what is happening right now. Right now is something we will never have access to for anything beyond our immediate vicinity. The present moment as a universal concept does not actually exist. There is only here and now, and then an ever-expanding region of not yet known. Betelgeuse lives in the not yet known. Maybe still burning, maybe already gone. The 700 years between us. Assume the explosion happens. Assume we see it, some night, bright enough to cast shadows. What comes next is not nothing. For a few weeks, maybe a few months, Betelgeuse will blaze in the sky with a brightness that defies easy description. At its peak, estimates suggest it could reach somewhere between -7 and -12 on the apparent magnitude scale. For reference, the full moon sits at approximately -12.7. So at its brightest, the supernova of Betelgeuse could rival the moon itself, a second light source in the night sky, one that does not rise and set but holds its position in Orion, fixed, unwavering, radiant in a way no star has been in recorded human history. It would be visible during the day.
You would be able to point at it through blue sky and afternoon light, a pinprick of impossible brightness sitting in the direction of Orion. Children who had never heard of Betelgeuse would ask what it was, and adults who vaguely remembered something about a star would struggle to explain. But brightness fades. All things fade. Over the following weeks, the supernova would dim. Over the following months, it would become a faint smudge, then an asterism in a catalogue, then a footnote. The light show would end. And what would remain, what would persist for thousands of years after, would be something else entirely. A supernova remnant.
The outer layers of Betelgeuse, blown outward at roughly 10% of the speed of light, would expand into space in an expanding shell of gas and plasma. At first too bright, then too diffuse to see with the naked eye, then slowly, over centuries, becoming a vast nebula, a glowing cloud of ionized material spreading across light years. We have seen this before. In the year 1054, Chinese astronomers recorded a new star in the constellation we now call Taurus. It was bright enough to be seen in daylight for 23 days and visible to the naked eye for almost 2 years.
Today, nearly 1,000 years later, what remains of that star is a structure called the Crab Nebula, a tattered luminous cloud roughly 11 light-years in diameter, still expanding, still radiating, still alive with the energy of the explosion that created it. The Crab Nebula is beautiful. Astronomers photograph it regularly, in X-rays, in optical light, in radio waves. It glows with shades of blue and red and violet, the remnant of a catastrophe that human beings watched happen, and then recorded in stone and silk. Betelgeuse's remnant will be similar, different in its details. Betelgeuse is a different kind of star, and the explosion will unfold differently, but recognizable in its broad strokes. An expanding cloud, a glowing monument.
A scar on the face of that region of space, and at the center of that remnant, if the physics works out the way most models suggest, there will be a neutron star. A neutron star is what you get when the iron core of a massive star collapses all the way down to a sphere of pure neutrons, roughly 20 kilometers across. 20 kilometers, the distance you might drive to reach the next town over. That is the diameter of something with more mass than the Sun. A neutron star's density is nearly incomprehensible. A teaspoon of neutron star material would weigh roughly 4 billion metric tons on Earth. 1 teaspoon. The weight of 40,000 aircraft carriers compressed into a volume smaller than a sugar cube.
If the remnant produces a pulsar, a rotating neutron star that sweeps beams of radio waves across space with every rotation, then astronomers 700 years from now will be able to listen to it. A regular pulse of energy ticking away like a cosmic clock, repeating, methodical, indifferent. The compressed core of a dying giant, spinning dozens of times per second, broadcasting its existence into the darkness. But the thing that most people will notice, the thing that will be obvious without a telescope, without a detector, without any scientific training whatsoever, is the absence. Orion will be wrong.
The pattern of stars that humans have recognized for tens of thousands of years, that appears on cave paintings and ancient temple ceilings and modern street signs, will be permanently altered. The left shoulder will be gone, not dimmed, not changed in color, simply absent, an empty space where something used to be. This will not happen immediately. Immediately, there will be the supernova itself, the blaze of light, the new star, the drama. But after the drama fades, what remains is the rearrangement, a constellation that has been a fixture of human visual experience for as long as humans have had visual experience, will be reduced. The hunter will be missing a piece of himself. Future astronomers will have to update their charts. Future teachers will have to explain to students why the asterism they learned no longer looks the way the textbooks show. Future poets will have to find new words for what Orion is. That is what a supernova leaves behind. Not just a nebula, not just a neutron star, also a rearrangement of the familiar, a change in the pattern humans have been projecting onto the sky for longer than writing has existed, and a reminder that the patterns we see are not in the sky. They are in us. The sky simply provides the raw material.
There is something that happens inside a dying massive star in the final seconds before the core collapses. Something that took physicists most of the 20th century to fully understand. The star makes iron. This is significant because iron is in a sense the end of the line. Stars generate energy by fusing lighter elements into heavier ones. Hydrogen into helium. Helium into carbon. Carbon into neon, neon into oxygen. Each fusion reaction releases energy, and that released energy is what holds the star up against gravity. The star is, in this sense, a constant negotiation between two forces: the outward push of nuclear energy and the inward pull of gravity. And the star survives as long as the nuclear reactions can hold gravity at bay.
But iron breaks the negotiation. Fusing iron does not release energy, it requires energy. So when an iron core begins to form at the center of a massive star, something fundamental shifts. The nuclear engine that has been running for millions of years reaches a terminus. The core continues to grow heavier as more iron rains down from the layers above. And at some point, when the core reaches approximately 1.4 times the mass of the Sun, gravity wins. The core collapses in less than a second. The shock wave that bounces back from this collapse is the supernova. But here is the remarkable part.
In the chaos of the explosion, in the unimaginable conditions of the shock front blasting through the star's outer layers, with temperatures in the tens of billions of degrees and neutrons flying in every direction, something creative happens. The heavy elements are born. This process is called the rapid neutron capture process, or the R process. Atomic nuclei are bombarded with neutrons so quickly that they cannot decay before capturing another neutron. In this way, nuclei heavier than iron, nuclei that no ordinary stellar fusion could ever produce, are assembled. Gold, platinum, silver, uranium, iodine, bromine. The heavy half of the periodic table, or a significant portion of it, emerges from the violence of an exploding star.
The same explosion that destroys the star also produces the elements that would eventually make their way into asteroids, into planets, into oceans, into living things. Consider what it means for destruction and creation to be the same event. Not consecutive, not destruction first and then creation after, but simultaneous. At the very moment the star tears itself apart, the conditions for making gold come into existence. The neutron flux required for the R process only occurs in the catastrophic environment of a collapsing core. You cannot have the gold without the collapse. You cannot have the elements without the death. The violence is not a side effect. The violence is the mechanism. For most of human history, we had no way of knowing this.
We looked up at the stars and they seemed eternal, or at least permanent on any scale that mattered. The idea that the stars were factories, that they were spending themselves on our behalf, converting hydrogen and helium into the heavier elements that would eventually become solid planets and living organisms. That idea required spectroscopes and quantum mechanics and particle accelerators, and the collaborative effort of thousands of scientists across the better part of a century. Fred Hoyle, the British astronomer who worked out much of the stellar nucleosynthesis theory in the 1950s, reportedly struggled to describe in words what it felt like to realize that carbon was forged in stars. He knew the physics. He had done the calculations.
And still, the full implication of it, that the carbon in every living thing had been inside a star before it was inside anything alive, struck him as one of the most vertiginous realizations a human mind could hold. The iron in your blood, the iron in the hemoglobin that carries oxygen from your lungs to every cell in your body, was made in a star. Not in our star, the sun, which is too small to produce iron in its core. In a larger star, long before our solar system formed, that iron was synthesized and then expelled into space when the star died. It drifted through the interstellar medium for perhaps hundreds of millions of years.
Eventually, the cloud of gas and dust that would become our solar system condensed. The iron was incorporated. It ended up in the rocky inner planets. It ended up in Earth. It ended up after billions of years of geological and biological evolution inside you. The gold in any piece of jewelry you might own almost certainly came from a neutron-star merger, a collision between two neutron stars, each itself the remnant of a supernova, or possibly from a supernova itself. Either way, the gold did not exist before stars existed. It was made in violence. It was distributed by violence. It arrived on Earth riding the debris of catastrophe. You are, in a very literal sense, made of dead stars. This is not a metaphor.
and in the shock wave, the blast of neutrons, the brief instant of our process nucleosynthesis, gold, platinum, and perhaps other elements we have not yet catalogued. These elements will be thrown out into space, carried on the expanding shell of the supernova remnant, and eventually, over millions or perhaps billions of years, they will become part of new interstellar clouds, new solar systems, new planets. It is possible, in an abstract but technically accurate sense, that atoms expelled by Betelgeuse's explosion will one day be incorporated into a living creature on some planet orbiting some star we have not yet discovered. That creature will not know where those atoms came from.
It will not know that they once burned inside a red supergiant 700 light-years from a small rocky planet where beings briefly existed who watched the night sky and gave names to the patterns they saw there. But the atoms will carry their history regardless of whether anyone reads it. History written in the structure of nuclei. History that does not require memory, does not require a reader, does not require anyone to know it happened. The universe keeps its own records at the atomic level, in isotope ratios and nuclear binding energies. A geochemist, with the right instruments, can look at a sample of ancient rock and read, encoded in the ratios of certain isotopes, the signature of a supernova that occurred before our solar system formed.
The explosion happened. The elements dispersed. The ratios locked in. The rock formed. The rock survived. And billions of years later, someone with a mass spectrometer decoded the message. The universe is legible if you know how to read it. And what it says, over and over, at every scale, in every medium, is that things end and other things begin from the ending. Stars die and planets form. Planets collide and moons form. Moons are bombarded and craters form. And in the craters, eventually, the chemistry of life finds a place to begin. Death in the universe is not an ending. It is a distribution event. Everything a massive star has built over millions of years of nuclear burning is flung outward when it dies, returned to the interstellar reservoir, made available again. The matter does not disappear. It just changes form. It disperses. It recombines. It begins again, somewhere else, in something else. Betelgeuse will die. And in dying, it will give. It has been giving all along. Every heavy element in your body is the inheritance from a stellar death that preceded you by billions of years. You did not ask for this inheritance. You did not choose it.
Orion is old, not in the way that a building or a city is old. Old in the way that a memory is old, something that exists because it has been passed forward continuously from one generation of minds to the next, never written down in any single place, always living somewhere inside the people who carry it. Archaeologists have found evidence that humans recognized the pattern of Orion's stars at least 32,000 years ago. A carved ivory tablet discovered in a cave in Germany, dated to the Aurignacian period of the Upper Paleolithic, bears a figure that some researchers interpret as Orion. The familiar shape of a human outline with the distinctive arrangement of stars matching the constellation we still call by that name today. 32,000 years ago, no cities existed, no writing,
no agriculture. The people who looked up at the sky and saw a pattern there, a human figure, a hunter, a shape worth carving into bone, were separated from us by every civilization that has ever risen and fallen. And yet they looked at the same stars, arranged in the same order, and recognized something in them. They gave it meaning. Think about the continuity that represents. Every person who has ever stood outside at night in a place where the sky was clear and dark has potentially seen Orion. Ancient Egyptians, who associated the constellation with Osiris, god of the dead. Babylonian astronomers, who called it the heavenly shepherd.
The sailors of ancient Greece, who used it to navigate. Medieval astronomers who catalogued it in manuscripts. Farmers in every latitude of the northern hemisphere who watched it rise with winter and knew what the season meant. And ordinary people. People who were not astronomers, not scholars, not navigators. People who simply looked up, maybe alone, maybe with someone they loved, maybe on a night when they were frightened or grieving or trying to find some sense of scale in their problems, and saw those stars and felt something about size, something about permanence, something about the distance between the human scale and everything beyond it. Betelgeuse was part of that. It is the left shoulder. The bright orange-red point that draws the eye and anchors the upper left corner of the constellation. It is, along with Rigel at the lower right, the first thing you see when you find Orion. It is the color that makes Orion interesting. The warm tint against the cold background, the suggestion of life, of burning, in an otherwise unvarying field of white and blue. And at some point, it will not be there. We do not know when. This is genuinely uncertain in ways that are not merely rhetorical. Estimates range from 100,000 years from now to already happened. The science is real, but imprecise.
The star is in its final phase of life, but the final phase of a red supergiant can last a very long time by human standards. It might not happen for 100,000 years, but it will happen. At some point in the future, perhaps while someone is standing outside, perhaps while everyone is asleep, a night will arrive in which Orion looks different. Maybe there will be the blaze of the supernova first, the weeks of impossible brightness, the new light in the sky. Or maybe, if enough time has passed and the explosion happened long ago, the change will simply be evident. A star that was there will not be there. The pattern will be broken. The hunter will have only one shoulder.
And then, over years and decades and centuries, the supernova remnant will expand. The neutron star at its center, if there is one, will spin and pulse. The expelled matter will disperse into the interstellar medium. And where Betelgeuse once was, where that orange-red point of light once anchored the upper left of a constellation, humans have been recognizing for at least 32,000 years, there will be a faint, diffuse glow. Eventually, even that will fade, spreading out below the threshold of naked eye visibility. And then, for anyone standing outside looking up at that part of the sky, there will be simply nothing. Empty, dark.
A gap in the asterism that the human visual system will keep trying to fill, the way the brain keeps trying to reconstruct a face from an incomplete photograph. Orion will adapt. Not because the sky adapts, the sky does not adapt, but because humans will adapt the story. They will redraw the figure to account for the missing star, or they will acknowledge it as a wound, the way a constellation can carry its history, or future generations will have simply never known the shape as it was, and will see the new arrangement as complete, as normal, as the way things have always been. There is something slightly vertiginous about that last possibility. People who have never known the shoulder.
People who look up at Orion and see 3 belt stars and 2 feet in one shoulder, and that is their Orion. That is the whole Orion. They will have no sense of absence because they will have no memory of presence. The same thing has happened before, on other timescales, for other reasons. Stars shift over millennia because of a phenomenon called proper motion. Each star has its own velocity through the galaxy, and over thousands of years those velocities rearrange the constellations into entirely different shapes. The Big Dipper, recognizable today to anyone in the Northern Hemisphere, will look nothing like a dipper in 50,000 years.
It will have sheared apart, with some stars moving one direction and others moving another, until the familiar pattern dissolves into something unrecognizable. No one living 50,000 years from now will mourn the Big Dipper. They will not know it as a thing they lost. They will simply have their sky, as we have ours, and their sky will seem to them as natural and complete and permanent as ours seems to us. The loss is only legible to those who know what was there before. This is how constellations work. They are not fixed features of the universe. They are collaborative fictions, patterns agreed upon by enough people for long enough that they begin to feel real. Orion is not a hunter.
Orion is a handful of stars at vastly different distances from Earth that happen, from our particular vantage point, to form a shape the human visual system interprets as human-like. The arrangement is an accident of geometry. The meaning is entirely ours. The universe has no Orion. The universe has hydrogen-burning stars and helium-burning stars and iron cores and supernovae and remnants and neutron stars. It has distances and timescales so vast that the word vast is inadequate. It does not have constellations. Constellations are what we bring, and Betelgeuse has been part of what we brought for a very long time. It is one of the brightest stars in the night sky, one of the most studied, one of the most recognized.
Children learning the constellations for the first time find Orion early, because Orion is impossible to miss. And within Orion, they find Betelgeuse, that warm, slightly orange, unmistakable point at the top left. And they are told that it is a red supergiant, that it is enormous, that it is dying, that someday it will explode. And for a moment, standing outside, looking up at it, they hold that information and look at the star and try to reconcile what they are seeing with what they have been told. A point of light, soft and ancient, and also a dying colossus, 700 light years away. Both things simultaneously.
That gap between what the eye sees and what the mind is told is where astronomy lives. It is what makes astronomy strange. You can know all the numbers and still stand outside and look up and feel the inadequacy of the numbers. The numbers don't replace the experience. The experience persists alongside the knowledge, and the two never quite merge. Betelgeuse is not going to explode tonight. Probably not in your lifetime.
almost certainly not in your children's lifetimes. It may outlast everything built in this century. It may outlast the memory of the civilization looking at it now. Or it may have already exploded, and the light is on its way. That is the thing that stays with you, once you have really understood it.
The light is either still coming from a living star, or it is the last light, the light that left before the explosion, before the collapse, before the final second when everything that Betelgeuse was became a shockwave expanding into nothing. And there is no way to tell the difference. The photons look the same either way. The orange glow looks the same. Orion looks the same. We have been looking at Betelgeuse for 32,000 years, maybe longer.
We have given it names in dozens of languages, assigned it roles in dozens of mythologies, pointed instruments at it that would have been unimaginable to the people who first noticed the warm color of that particular star in that particular part of the sky. We have watched it dim and brighten. We have seen it with our naked eyes, and with telescopes, and with radio arrays, and with neutrino detectors. We have measured its diameter, mapped its surface, modeled its core. We have written papers about it, and given talks about it, and lost sleep wondering whether the great dimming of 2019 was finally the beginning of the end. And still, when it goes, it will catch us by surprise. Because that is what light delay does.
That is what 700 years of silence does. It hides things. It holds things back. It makes the universe's most dramatic events arrive without announcement, without warning, as a sudden presence where there was no presence before. The shoulder of Orion has been part of the human sky for as long as the human sky has been looked at by human eyes. It has been a fixed point in a world of change. Empires came and went beneath it. Languages were born and died beneath it. Everything that has ever been called civilization happened beneath a sky that contained Betelgeuse. And one day, that will no longer be true. One day, someone will look up, and the pattern will be wrong. The hunter will have one shoulder.
The asterism that has been continuous for tens of thousands of years will have a gap in it, and the universe will not notice. The universe does not arrange stars for human convenience. It does not hold constellations in place because we find them comforting. It moves on its own schedule, at its own pace, according to its own physics. Betelgeuse is running out of fuel, because that is what massive stars do. When it explodes, it will not be doing it for us. It will simply be obeying the same nuclear physics that has governed it since it formed 8 million years ago. We are observers of something that would happen exactly the same way whether we existed or not. And yet we look. It moves on its own.
We built our calendars around the rising and setting of Orion. We navigated ships by it. We told stories about the hunters standing in the winter sky. We found something in that arrangement of light that felt meaningful, felt like a message, felt like something meant for us. It was not meant for us. Nothing in the sky is meant for us. And yet we keep looking, and the looking keeps meaning something. And that gap between a universe indifferent to our existence and a species that cannot stop finding patterns cannot stop reaching for significance, cannot stop looking up. That gap is perhaps the most human thing there is. Betelgeuse is not watching us back. It does not know we are here.
It has been burning for 8 million years, and it will either burn for a little longer, or it has already stopped, and the light from that stopping is on its way, and we will not see it coming. And when it arrives, it will reshape the night sky that every human who has ever lived has looked up at, and after the blaze fades, after the remnant dims below the naked eye, after the neutron star spins on in radio silence, there will be a dark spot in Orion where the left shoulder used to be. And the people looking up at that sky, if there are people, will find new stories to tell about the shape that remains. As people always have, as people always will.
Because that is what we do with the dark. We fill it. But Betelgeuse will not be there to be filled. It will be gone, scattered across light years of space, its iron in clouds of gas, its gold in the deep vacuum, its last light already past. And the hunter will stand in the winter sky, as he always has, looking up at nothing in particular. One shoulder bare, one arm raised, the belt of 3 stars still crossing his waist, the nebula still glowing below. The same sky, and not the same sky, the same dark, and a little darker. One day, the shoulder of Orion will simply not be there anymore.